All right, so in the previous video where we ended was we showed that if you have a power series that's convergent on some interval of convergence where the radius of convergence is positive, so non-zero, then you can differentiate or integrate that power series term by term. Here's the theorem that stated that. We're not proving this theorem here. It requires more advanced techniques than we're really going to get into, but you can prove this. We're just going to use it. So what we want to do is use this theorem to express this new function, 1 over 1 minus x quantity squared, as a power series. Now, at first glance, this looks pretty close to the power series that we started with at the very beginning of this section, this guy right here, right? But the techniques that we used in the previous examples to come up with a new power series from an old one don't really work here, because there's more going on than just substituting something new in for x. In fact, this is literally this function squared. So if I wanted to find a power series for this, one way is to take the power series for 1 over 1 minus x and then try to square it, which means multiplying it to itself. Except we haven't talked about how to multiply two power series together yet. And we're not going to in this section. That'll come later. So a different approach that we could take is to notice that there's another relationship between this function and the function 1 over 1 minus x. In fact, 1 over 1 minus x squared is the derivative of 1 over 1 minus x. And you can verify that pretty easily. I'm not going to do that here because that's a simple one to do. Just use the chain rule. But knowing that and knowing what the power series for 1 over 1 minus x is says that this can be differentiated by instead differentiating its power series. 1 plus x plus x squared plus x cubed plus and so on and so forth. And then in addition, our theorem up here says that I can do this differentiation term by term. So differentiate the 1 and get a 0. X, when I take its derivative, gives me a 1. X squared becomes 2x. X cubed becomes 3x squared. I would have had an x to the 4th after that, so that would have given me 4x cubed, and then so on and so forth. This power series is the representation of this function as a power series. And not only that, this will have the same radius of convergence as this one, which is 1. So that is very useful because it did not take much work to get to an answer by recognizing the relationship between those two functions as one as the derivative of the other. Let's see if we can do more with this theorem, kind of get more power series. So here's a function that looks nothing like the other functions that we've been dealing with. We've been dealing mostly with functions that are rational and look somewhat close to the function 1 over 1 minus x. And then we do some substitutions or we multiply by something to compensate. This looks nothing like any of those. But the natural log function, we know, does have a relationship to a specific rational function. So the natural log of 1 plus x is an antiderivative for 1 over 1 plus x, dx. Okay? This guy is very close to this guy, except notice the only difference is I have to substitute a negative x in for the x so that my minus changes to a plus. So this will have a power series equal to 1 minus x plus x squared minus x cubed plus ... It goes on forever, right? So this and this are equal to each other because this is the power series for this guy. And again, I'm skipping the step where I'm showing the substitution happening, but I'm literally just plugging a negative x in for the x in the power series on the first page of these notes. This, according to that theorem that we just talked about, can be integrated term by term. And you do need to be careful because with integration, we do get a constant of integration. So there is going to be a c that comes from here. But then for the rest of this, plus that 1 becomes an x, minus x becomes minus x squared over 2, plus x squared becomes x cubed over 3, and then minus x to the 4th over 4, and so on and so forth. Okay? Now we don't really want to stop here because that constant of integration can be solved for. Remember, this can't be an arbitrary constant because I'm saying that this power series is equal to this specific function. So whatever I plug in for x over here, I should get the exact same thing if I plug that number in for x over here. And the most logical thing to try plugging in for x is x equals 0. So if I plug x equals 0 into the left-hand side, I get the natural log of 1, which is equal to 0. If I plug 0 into the right-hand side, all of these terms go to 0, and all I'm left with is c. So this shows me that that constant of integration is actually equal to 0 if these two things are supposed to be equal to each other. So I can get rid of that c if it's equal to 0, and now I can write the natural log of 1 plus x is equal to x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus and so on and so forth. Or in summation notation, let's make that an I. Let's make that an n. The sum is n goes from 0 to infinity. I just realized I think I put some things in summation notation in previous examples where I called this an I, but then I used an n over here. So I'm going to go back and fix some of that in a second. Let's make that an n. And this is going to be, it's an alternating series, so I do need a negative 1 to the n here. And then I'm going to have an x to the n plus 1. And the reason I need an n plus 1 there is because if I plug a 0 in for n, my first term will be n x to the first power, which matches what I'm seeing here, over n plus 1 down here. So that n equals 0, when I plug it in for things here, would give me a 1 for my first denominator, a 2 for my second, and so on and so forth. Now that works, but this is an example of a series where it might be worth re-indexing. So what it means to re-index a series is to change its starting point. Instead of starting at 0, it might be preferable to start at 1. And then what happens is my n plus 1 becomes an n, my x to the n plus 1 power becomes an x to the n, and then my negative 1 to the n becomes negative 1 to the n plus 1. Notice that that would match term for term everything I would get from this series if I started at 1 instead of 0 over here. I'll let you verify that. This right here is the power series representation for the natural log function, and its radius of convergence is the same as the radius of convergence of this function. So the radius of convergence is still equal to 1 in this case. This didn't ask for it. I'm just making a note of it here. Let me go back to some of my previous examples and see, because I'm pretty sure I've been using an I in some of my summation notation where I should have been using an n. Yep, I see that here. So this is from the previous video. Let's change that guy to an n. That guy needs to become an n, and that guy needs to become an n right there. And then did I do that anywhere else? Let's see, not there, not there. Okay, I think it was all on that page. Thanks for bearing with me for making that correction. Let's do another one. I want to find a power series representation for the tangent or the inverse tangent function. So this guy is going to be very similar to what we did in the previous example, because I have a relationship between a particular rational function and the inverse tangent function. So looking for that, I know that the inverse tangent function, inverse tangent of x, is equal to the antiderivative of 1 over 1 plus x squared, or at least it's an antiderivative for that function. I should include a dx in there as well. Okay, so that function 1 over 1 plus x squared, we have already found a power series representation for that. It's this guy, 1 minus x squared plus x to the 4th minus x to the 6th, and so on. So that means I can represent that function in that form. 1 minus x squared plus x to the 4th minus x to the 6th, and so on, dx. Okay, at this point, I can represent that, or I can integrate this term by term. So what that means is I get my constant of integration, c, and then, sorry, not parentheses. equals c plus, I'm going to get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on and so forth. So now, just like in the previous example, I am going to want to figure out what c is equal to. So I can pick a value of x and plug it into the inverse tangent function, and then also plug it in over here and make sure that these two things come out equal to each other. The best choice, again, is x equals 0, because on the right-hand side, all of these terms just go to 0, leaving me with just x. On this side, I get the inverse tangent of 0, which I know is equal to 0, and also equal to c. So c must be equal to 0, which means I can just eliminate it. So the inverse tangent function is equal to this power series, x minus x cubed over 3, plus x to the 5th over 5, minus x to the 7th over 7, and so on and so forth, which we can write in summation notation as the sum where n goes from 0 to infinity of it's x to some power over a denominator that matches that power. So you notice this could be written as x to the 1 power over 1, x to the 3rd over 3, x to the 5th over 5. I want to account for the fact that all of these powers and denominators are all odd numbers. One way to get an odd number is 2n plus 1. Whoops, I'm off the screen there. So if I plug 0 in for n, I get x to the 1 power. And then I want my denominator to be the same thing, so I'm going to put a 2n plus 1 down there as well. If I plug a 1 in for n to get to the next term, I'm going to have 2 times 1 plus 1, that's 3, and then a 3 in my denominator, so that matches as well. One thing I did not account for, which I need to, is my alternating factor here. So I have negative 1 to the power of n there as well, because this is an alternating series. I kind of forgot to put that there at first, so I squeezed it in, but that's what that is. So this is the power series for the inverse tangent function. And we got there by taking a series that is easy to find a representation for as a power series, because we've already done that. Recognize the fact that when I integrate it, I get the inverse tangent function as a possible antiderivative, and then solve for that arbitrary constant there. But that reveals that the inverse tangent function has this power series representation. It's very useful. All right, let's do one last example to see where we might use a power series to approximate a definite integral, because this is one of the many uses of these power series. So here we want to evaluate the integral from 0 to 0.3 of the function x squared over 1 plus x to the 4th. And we want to evaluate that to 6 decimal places. So correct or accurate to 6 decimal places is what that means. I might be able to do this integration by finding an antiderivative. Maybe I can use like some kind of a partial fraction decomposition or some kind of clever substitution or something like that. But it might be kind of difficult to do that also. And in some cases, none of those techniques might work. So rather than rack our brains over trying to figure out a substitution or something to solve this accurately, I'm instead going to take my integrand and represent it as a power series and then do my integration term by term. Now this particular function, I believe we have already found, or did we? No, we did not find a power series representation for this. That's okay. We can find one without too much trouble. So what I'm going to do, we have x squared over 1 plus x to the 4th. I'm going to pull the x squared out front, and the 1 plus x to the 4th I'm going to write as 1 minus negative x to the 4th. And again, we've seen this before. We know why we're doing this. I can go back to that original power series representation for 1 over 1 minus x and substitute negative x to the 4th in for that x. So what that's going to give me, I can't forget that this x squared is out on the outside here. I'll get 1 plus that thing, negative x to the 4th, plus that thing squared, plus that thing cubed. Keeps going. Now let's simplify a bit. So I have this x squared here, 1 minus x to the 4th plus x to the 8th minus x to the 12th plus dot, dot, dot. Okay, so simplifying those. Then I can take that x squared and multiply that in as well. So I'm going to get x squared minus x to the 6th plus x to the 10th minus x to the 14th, and then so on and so forth. Okay, so if I want to find this integral right here, the definite integral from 0 to 0.3 of x squared over 1 plus x to the 4th dx is the same thing as the definite integral from 0 to 0.3 of this power series, x squared minus x to the 6th plus x to the 10th minus x to the 14th plus dot, dot, dot dx. Now, one thing that we would need to be careful with here is to make sure that the power series that we are using here is compatible with the limits of integration. And what I mean by that is that this power series only converges if the absolute value of x is less than 1. Because that gets carried over from the radius of convergence from our original power series, 1 over 1 minus x, when we solve for that. And it's easy to show that this has the same radius of convergence. So the interval of convergence for this power series is the interval that goes from -1 to +1. And if you notice, the interval that I'm integrating over is a subset of that integral, or that interval. So in other words, all of the numbers between 0 and 0.3 are in the interval of convergence for this power series. So this is valid to do this. If I had limits of integration that went outside of that interval, then I couldn't do this. But moving forward, we need to integrate this term by term. X cubed over 3 minus x to the 7th over 7 plus x to the 11th over 11 minus x to the 15th over 15 plus dot, dot, dot. And then we evaluate this from 0 to 0.3. Now notice if I plug this lower limit of integration in, I get all zeros. So that contributes nothing. I really just need to plug the 0.3 in. This is equal to 0.3 cubed over 3 minus 0.3 to the 7th over 7 plus 0.3 to the 11th over 11 minus 0.3 to the 15th over 15 plus dot, dot, dot. All right. Now, obviously, if I could find a way of, finding the actual sum of this series, then there would be no need for an approximation. Like if I could show that as a geometric series or something like that, and then use that formula for the sum of the convergent geometric series, I'd be in good shape. But it's not a geometric series, and I don't know off the top of my head what this would converge to. So we have to settle for an approximation, and we're being asked to approximate it to 6 decimal places. Now notice that it's an alternating series. We have seen back in section 11.5 that if you want to approximate the sum of a series that's an alternating series, then the remainder term for the nth partial sum is always going to have an absolute value that's less than the next term that would come after that sum. So for example, if I wanted to sum the first 3 terms in this series, 1, 2, 3, when I do that, the remainder term, remember the remainder term shows me how far off from the actual sum of the series I am when I use that approximation. The remainder will have an absolute value that's less than this term here when I take its absolute value. So what I'm going to do is compute some of these and figure out when is the first term in this series, or where do I find the first term in this series that gives me 6 zeros after the decimal point. Because if the remainder has 6 or more zeros after the decimal point, then that indicates that my approximation is within 6 decimal places of the actual sum of the series. It turns out that happens very early. It's the 3rd term. If you compute 0.3 to the 11th power over 11 in a calculator, you get a number that's approximately 0.12345 zeros, 161, and then it keeps going after that, but it rounds to about that. Before that, these numbers are small, but they don't have 6 zeros after the decimal point. This is the first one for which that occurs. So by that technique for approximating alternating series, this is I think of this as like the n plus 1th term. And so I only want to sum the first n terms. I only want to sum the terms that come before it, because that sum will have a remainder term that's less than this number right here. So to approximate that series, I just need to do 0.3 cubed over 3 minus 0.3 to the 7th power over 7. And that will give me the approximation that I want to that desired degree of accuracy. Use a calculator for that. 0.008514 roughly. That's what that comes out to. Okay? That is the last example that we need to cover here. We are getting close to the end.